Well, thanks for having me. I mean, again, it's great to be part of a cool little niche like this, and I'm happy to share what I've learned. And thanks for the great introduction and the people that can be here live. So as Indy said, my name is Ytsma, and I split my time between planetary science and health data. But essentially, it all boils down to the same types of thinking. And the goal of my seminar is really to help answer this question: how do I make a good calibration? And good is obviously context dependent, but it's based on two things: your standards and your methodology. So for the standards, as we know, you would want to maximize the size and diversity of your data set to best represent an unknown that you could find. And here's what it might look like for classification. So in this example, this is a total alkali silica or TAS diagram for igneous rock classification. You see there's enough samples that basalt and rhyolite are really well defined with standards, but you couldn't be able to quantify or classify, phonotephite without adding more standards to your model. The same thing for quantification. Aluminum oxide here is well characterized at low and higher concentrations, but the model has no clue what something with concentrations between 3 and 11 weight% looks like. So it would not be a useful data set for that range. And just to boil down to say, machine learning is not magic. People often overestimate its power and will apply methods without really understanding how the models interpret the data. Yes, it's powerful, but it will only tell you what it's learned based off what you gave it. It's not able to fill in gaps in sampling for you. Of course, this goes back to context. If you only want to characterize 13 to 20 weight% alumina, then you're fine with these data. Whereas when you're picking the right method, there are several things you may consider before choosing a best option. And I think we all know that planetary science analyses, especially with spectroscopy, have historically relied on things like laborious peak measuring or fitting, specialty specific software, or complicated formulae that only a few people really understand how it works. The great thing about machine learning is there's a multitude of well-documented and open source resources that people can use to try out these models quickly and easily, like scikit-learn, which is a Python machine learning repository, which I use for all my modeling and requires some basic programming knowledge. And that's also, their models are also used by PyHat, the Python hyperspectral analysis tool, which needs no programming skill and was developed by NASA scientists for planetary research. And my non-coding coworker uses this exclusively for her research. So there's options. But now I've kind of described the framework of what makes a calibration. I want to describe my personal research background a bit to give some context for the decisions and the results I'll present. But these takeaways are relevant to modeling for many other types of spectroscopy and other sources of complex data. Then I'll describe how and why I chose the machine learning method that I use most often, and what methods might be better suited to other applications or types of data. Then I'll delve deeper into how the training data and calibration methodology can affect results. And lastly, I'll show how useful ML can be in situations where traditional methods are still prioritized, like XRF. So for people who don't know, laser-induced breakdown spectroscopy, or LIBS, is something that I'm experienced in, and it's a great example actually for working with complex data and planetary science. Quick background is that it uses a pulse laser to remotely ablate a sample surface, converting it to a plasma, which will emit photons from the sample that you can collect by spectrometers. So these atomic emissions are collected and form a pretty complex spectrum. From the UV, vis, and V near ranges is usually where it's collected. And what's great about it is that Spectra contains signals from basically the entire periodic table, which makes it one of the few techniques to reliably measure light elements like hydrogen and sulfur, as well as major elements in rocks like silica and aluminum. Also, because it's a remote sensing capabilities, it's really useful on planetary surfaces. And if you repeat laser pulses, you get the opportunity to analyze your sample at depth. So these capabilities have made it chosen to be on board the 2012 and 2020 NASA Mars rovers on ChemCam and SuperCam. And that's my application for it. However, it has to be said that LIBS spectra of rocks can be so complex that different elements interact within the plasma or they have overlapping emissions, which disrupt the linear relationships and makes quantification more difficult. So the source of my LIBS data comes from the mineral spectroscopy lab, which is led by Darby Dyer at Mount Holyoke College in South Hadley, Massachusetts. And it contains roughly 3,000 rock standards in the form of pressed powdered pellets, which include some rock matrices doped with up to 10 weight% of trace elements, which are marked in blue on the table, and the matrices are marked on the TAS diagram. So here's an example of what these pellets look like. On the sample tray, you can see actually the spots in a row where our LIBS have analyzed them. And we have 2 custom LIBS instruments built to replicate the ChemCam and SuperCam, including atmospheric chambers, so that we can analyze these in Mars atmosphere, ambient air, and under vacuum. So this setup with our uniquely large and diverse set of standards have made our data sets incredibly powerful for understanding not only geological quantification with LIBS, but influences to machine calibration models in general. So one problem with machine learning being so accessible is that people will apply models without really understanding how they work or what's best suited to their data. So the right choice depends, as always, on context, as well as the type of data you're working with. But broadly, you can classify them between linear and non-linear methods. So these are the methods that I test, which are all available on scikit-learn, and also what's available in Pi-hat. So those in the depends column can either be linear or non-linear, depending on the kernel function you provide. So a good example to start with understanding linear versus non-linear is the most basic linear regression, which is univariate modeling, where I'm sure everyone's seen this before. You plot a single value, often the signal intensity or a peak area against the thing you're looking to predict. You get a line of best fit, and that becomes your calibration. So here's an example I quickly made with some SuperCam Mars data on the strong lithium peak at 670 nanometers. And if we expand this to a machine learning method, you're no longer looking at just a single signal, or what I really should say, multivariate analysis is the difference here. And multivariate analysis with machine learning means we let the model decide where the important points in the spectrum are, not just the ones that we already know about. So PLS is an example of a linear method that's used often with spectroscopy because it shows these relationships and it generates good accuracies. So here you can see the model coefficients for the lithium model, which independently identify the 670 nanometer peak, as well as the other regions of interest that we could look into more for research. Another common option is lasso, which the other type of linear models you want to think about are sparse or not sparse. So lasso is a sparse model, which means it ignores the regions of the data it finds noisy or unimportant. And it's not as common to want sparseness in spectroscopy because you lose the big picture understanding of the relationships you get, like with PLS. But it is useful if you want to prioritize regions of your data or trimming down input variables in other contexts, like in health, because if you think about it, the model is taking each point in the spectrum as an independent variable. And if your independent variables are all different and you want to know which works and which doesn't, a sparse model would make sense. You may also notice that the lasso model did not find that 670 nanometer peak, which is a problem with sparse methods. You might miss out on important features due to the random selection of the correlated areas. So then if you look at nonlinear methods, they use a completely different approach. Random forest, like other randomized ensemble methods, throw the kitchen sink at the problem and we'll just make a bunch of random models, average the prediction of all of them at the end until you minimize the error to suit your application. Or K nearest neighbors, it's looking at the K most similar training data to the unknown, average those values, and get the result. And these methods can lead to a great performance, but they often overfit to the data, and it's really hard to interpret how the model actually digested and used the data. And you can try to avoid overfitting by having more randomness or looking at more samples before you make a decision. But I find nonlinear methods less useful for data that are based on linear relationships like most spectroscopy data is. So the real question, how do you choose a machine learning method? As always, it's a decision between performance, interpretability, and context. So the process for making a calibration, which I won't go through, results in 3 types of accuracy assessment, which I put in bold. And for quantification, these are often expressed as root mean squared errors or RMSEs. Same approach for classification, just different metrics. If we compare the results for the models I listed earlier, using a different, not a LIBS data set, but what is it, mid-IR, it's very similar performance. We quickly see 2 trends in the results. Those with big splits between the training, the orange, and the testing, the gray and blue errors, and those that have more agreement. So this first case is classical overfitting. You prioritize a low training error and you're going to get high test errors. We want something where the values are more in agreement. And it makes sense that the training error, again in orange, is always going to be a bit lower, a bit better than an accuracy on the unseen data. So then how do I choose from these 3 methods? I want a linear model that is not sparse because I want to understand the spectra better for my research. So I chose PLS over Ridge and ElasticNet, which are both sparse models. So just to say, yeah, there's a lot of things you can consider, but if you think about it, what you want from your data and what you're doing with it, it makes it easier. Moving on to how data affect model accuracies. Well, if you remember, the goal of any calibration is to choose standards that are most representative of the unknown. Therefore, a model should improve as it gets bigger and more diverse. So because we have all this data, we actually studied this within our ChemLibs data set, and we varied the size of the training data from 75% to 1/200th of all of our standards and tested on the rest of the data set. So as expected, the more data you train on, or if we're going left to right, the less data you train on, the worse your accuracy gets, or the higher your error in this case. So this is where context comes in. For mining, an unknown core might be from a well-characterized region. So while your analyte concentration isn't known, your rock type may be. So you can limit your model to suitable standards sufficiently. However, for planetary applications, the unknown is often very unknown, and it can be hard to access sizable and diverse training data sets. So the question is, how do you best use your data to predict what you want? And one common approach for getting creative with training data is called submodeling. Submodeling is where you classify your data by other means, for example, like a spectral peak ratio, something that we don't need to know about the data already, and we can make a suite of individual submodels of each criteria. Then you would identify which model to use on the unknown via the same process to get the corresponding prediction. So the question is this worth it? In my opinion, no. Not only is making and deciding, formatting submodels a lot more work than making one model. While individual submodel results may seem way better, they are often vary widely and are just as bad in the other direction. So they end up having a comparable average performance to a single generalized model. And larger models are also more robust. So splitting the data into smaller pieces and smaller models opens them up to overfitting or misclassifying an unknown and ends up being counterintuitive. So actually, my coworker Kate has put out 2 really interesting pieces of work looking at this, linked on the slide, splitting by silica ratio, silica concentration, seeing if that works, didn't. And also combining a bunch of different laser power data into one massive model. And it did better than if you separate by laser power. So it's really convincing that more data are better. If you can get them, put them all together and let the machine learning do the trick. Lastly, I want to propose machine learning as an alternative method that you can apply alongside accepted calibrations that have high performance. So an easy example for this is fundamental parameters, or FP, which is a method used to quantify XRF spectra. And FP models are based on the fundamentals of atoms and therefore don't rely on training data to make predictions. They're just a human-derived calculation that's customized to the instrument setup. So you can see this beautifully defined relationship in this peak of potassium oxide in our standards from portable XRF data. So you could think, can machine learning really improve on something that's so accepted as this? And it depends. So these data are from a study I'm about to submit that compares PLS models to fundamental parameters results from the instrument using a portable XRF. And they show pretty similar results overall. And there are some strengths to both methods, and machine learning is actually much better at low concentrations of trace elements. But what I find to be important is not only the accuracy, but the context, as I've discussed before. Because FP calculations are instrument specific and it's not clear to the users how exactly the instrument makes its predictions. With machine learning, you have all this ease and accessibility that you can quickly make a model and get a second opinion on what the instrument output is giving you. So it's just, even if it's not a massive improvement, it's an alternative method that can give you more information about your data. And in conclusion, as we know, ML is very powerful and well suited to planetary applications. It's easy to access and interpret due to public code and documentation. And I would really recommend you take the time to truly understand which methods you test and how they're suited to what data you're using and what you're using them for. And I think this is key. It's imperative to devote resources into developing a large and diverse suite of standards, especially for planetary science, or when you can't get one or find one, understand the limitations of the data set you are using. And lastly, that machine learning can be used as another option to well-regarded other calibrations. So thank you. Nice to see you from gloomy Scotland. It's been great to discuss this, and I'm looking forward to any questions you might have.